Hi there, this is Dr. Satish, Assistant Professor at British Applied College. I welcome you all to this video lecture. This video is for Level 4 Unit ENG208 Mechanical Principles meant for Level 4 Pearson Higher National Diploma in Mechanical Engineering. Now, in today's video, we will be trying to solve reaction forces for simply supported beam with uniformly distributed load. In my previous lecture, I solved calculating reaction forces for simply supported beams with point loads or concentrated loads. In today's lecture, we will go for uniformly distributed load. Now, you all can see the screen where this is my uniformly distributed load. Okay, so the unit, please note the unit. The unit is kilonewton per meter. Okay, if I take a point load, in my previous lecture we discussed about point load with simply supported beams. This point load is the unit kilonewton. As per my knowledge, always study the quantities with units. That will give you in-depth picture. Okay, so now here I have to convert this to kilonewton if I want to use it in my force equations. Okay, so I will look into it. I will explain about it later. Now, to solve any, like I said in my previous lecture, to solve any reaction force problems, we have to use equilibrium equations. Okay, so the equilibrium equations for 2D is, I will write my equilibrium. I will just copy it from my previous lecture. So the equilibrium equations in 2D, okay, it will be three things. Force along the x-axis, summation of force along the x-axis is 0, summation of forces along the y-axis is 0, and summation of moments, okay, it is 0. Now, in this case, first we don't have any, if you note our free body diagram, we don't have any horizontal forces, all are vertical forces. I have two reactions because it is a simply supported beam, and this force, okay, for the uniformly distributed load, it is acting downwards. Okay, so I don't have any horizontal forces, so I will not be using this equation. Okay, so now if I use the second equation, summation of forces along the y direction equal to 0, okay, I am going to take all the forces that is acting upwards as positive. Now let me write the equations. So I have three forces now. Okay, I have the reaction forces. I will take them as positive because they are acting upwards. And if you closely watch this, as I said early, okay, this is in kilonewton per meter. Fine. So this is a weight density. Okay, so to convert this, to use this in my equilibrium equation, I have to multiply by the length. Okay, so this load is acting along 3 meter length, as you can see. So I will multiply this by length. So 6 kilonewton meter into 3 meters. So finally I will get 18 kilonewton. Okay, and the sign, please note the sign. This is acting downwards. So what I have to do? I have to use a negative sign. So my final equation will be RA plus RB is equal to 18. This will be my equation 1. Okay. Now I will be using the second equilibrium equations. Always remember, if there are n number of unknowns, then we have to use n number of equations. Okay. So we have two unknowns here. So I will be using, I have to use two equations. So I go for the second equilibrium equation. Summation of MA is equal to 0. Now let me consider the point A. Yes, usually I will consider A. Let me consider the point A. So all the moments acting at point A is equal to 0. As I said early in my earlier lecture, if a point load, if a force is acting at a point where we have to find the moment, okay, it will not cause any moment. Please understand. Imagine if a force is acting away from the point of consideration, then this will cause a moment. Okay, this will cause a moment in the sense it will create a rotational effect. Okay, now if the force is acting at the point of consideration, it will not cause any movement, but it can translate. Okay, it can go up, translate, the body can translate, but movement no. Fine. So the movement is caused by two forces. One is uniformly distributed load. Okay, the second one is reaction force RB. Okay, so I have to consider that, and for this I will consider anti-clockwise as positive. Okay, you can consider anyway, either ways, no problem. So this, if I fix my point at A, and this is creating, what type of movement it will create, what the type of rotation or effect it will create is along the clockwise. Okay, so I will give a sign, negative sign for this. I will give a negative sign, and always the moment is force into distance. Okay, so the total force acting because of this uniformly distributed load is 18. Just now we saw this. Okay, the total force acting because of this uniformly distributed load is 18. Now I will write this total force 18 into the distance. When it comes to distance, you have to just closely look into it. Now this is spread along 3 meter. Okay, you all can see this is spread along 3 meters. So the intensity of the weight of the whole weight will be, okay, if I consider if I want to convert this into equivalent point load, okay, then it will act exactly at half. Please understand, it will act exactly at half. So this will be at 1.5 meter away from A. Please note this. This will be 1.5 meter away from A. So 18 into 1.5. Okay, negative direction, because as I told earlier, this will create, if I hold my point here, because of this load it will create a clockwise rotation. Okay, because I consider anti-clockwise as negative. Now the other forces RB, if I apply the load here, fixing my point at A, it will create an anti-clockwise rotation, and that I give positive here. So I give positive here, RB into, what is my load here? My load is, my distance is 5 meter. Okay, so RB into 5 is equal to 0, thereby RB is equal to 18 into 1.5 by 5. If I quickly look at my calculator, where's my calculator? Here it is. Okay, now okay, so if I quickly look into the calculator, then what I have here is 18 into 1.5 divided by 5, so 5.4. okay, so here we have 5.4 kilonewton RB. okay, and the total, I am going to substitute this. Okay, substitute this equation 2 in 1. So what happens is, so my RA, I can find my RA as 18 minus 5.4. So 18 minus answer 12.6. So it is 12.6 kilonewton RA. Okay, so to justify our answer, we can understand, if the load is acting towards RA, see the load is acting towards RA, so definitely it will have higher reaction force compared to RB. So this is almost 12 and this is almost near to 6, so twice the amount of reaction forces. So this is how we solve reaction forces for simply supported beams with uniformly distributed load. Okay, so this is my uniformly distributed load. Thank you guys. Let me see you all in the next video.